Here we have a solid disk with a given mass and radius, and it's free to rotate on a frictionless axle through the center. The disk is initially at rest, so it's not moving at all, but we have a bullet that comes flying in. This bullet hits the disk and becomes embedded in the disk. And you can imagine the bullet's going to come in and hit the disk, and then as a result, the whole thing is going to start rotating. And we want to know what is the angular velocity of the disk. And so what's happening is the bullet is flying through the air. From the instant before the bullet hits the disk to the instant after, there's no real outside forces affecting the bullet. There would be air resistance and that sort of thing, but over such a short period, we can ignore, the effects of any of those outside forces, right? This is we talked about this calling the impulse approximation, looking at linear momentum, and we have the same idea here. We would have forces where the bullet would be applying forces to the disk. If the bullet is applying a force to the disk would be applying a force back to the bullet. So there would be forces and momentum acting, or forces and torques acting on either object. That would be very complicated. But if we're clever, and if we define the system as the bullet plus disk system, then all of those forces of interaction between the two are interior forces, they're internal forces that are not going to change the overall momentum or change the overall angular momentum of the system. So basically, this is a collision. The same way that a collision made us want to use momentum, here we have a collision plus rotation, so that makes us want to use angular momentum. And the system we're going to use is going to be the angular momentum of the bullet plus disk system, so that we don't have to consider the forces of interaction between those two objects. So there's no other torques acting on the system. The only forces are these two interacting with each other. There'd be some forces with the axle here, but those forces would not produce a torque. So we could say that angular momentum is going to be conserved in this case. Initially, we're going to have an angular momentum for the bullet and an initial angular momentum for the disk. And then afterwards, the two of them are embedded together. So we'll say that there's going to be one net angular momentum at the end. We're told that the disk is initially at rest, so it's not going to have any angular momentum, right? For the disk, we would say that its angular momentum is I times omega, but if omega is 0 because it's at rest, then we wouldn't have any angular momentum there. The bullet is moving in a straight line, right? The bullet isn't rotating around a axis of rotation. I mean, technically it is, but we're ignoring the spin of the bullet. It's not going around in a circle, it's going in a straight line. But the bullet has angular momentum in that it has linear momentum traveling along its line of motion. And we know that it has angular momentum associated with that linear momentum. The other way of putting this equation was mv r sine of phi. Technically, what we would want to put here would be, this would be r. We would have the momentum of the bullet, and we could find the equivalent, we could find how much equivalent angular momentum that amount of linear momentum would represent. What we can do, though, is instead of doing this cross product, instead of worrying about angles so much, this r sine phi, in this case, phi is going to be, should be the angle from should be this angle here. And the long story short is that r sine phi is this distance here. Essentially, r sine phi is similar to the moment arm when you are looking at torque. So you can look at r, the distance, and the angle, and look at all those things separately, but you can also combine all of them into one view, and again, look at it this way. The bullet has a certain momentum. That momentum is acting along this line, and the r sine phi term is basically looking at how far the momentum passes from that axis of rotation. And we know what this value is. It's r over 2, which is going to be 0.2 meters in this case. So the initial angular momentum is carried by the bullet. Even though it's traveling in a straight line, it has angular momentum relative to this axis, because if it hits the disk, it's going to tend to cause rotation that way. So we have mv. M is the mass of the bullet. It's 10 grams. So we'll put that in kilograms. Its v is the velocity of the bullet. That's 500 meters per second. And r sine phi is 0.2 meters. Notice as well, the bullet is going to tend to cause clockwise rotation. So we'll just call that negative because of the relative directions of r and p in that case. After the bullet collides with the disk, they're going to be stuck together. They're going to be moving as one object. And so the angular momentum at the end, we would say, is the moment of inertia of one object, and that one object is rotating with some final angular velocity. The moment of inertia of the object is going to be the moment of inertia of the disk, which is rotating around, plus the moment of inertia of the bullet, which is embedded, and the bullet is now following a circular path as well. This question isn't worded terribly well, but we're going to assume that the bullet is this distance r over 2 from the axis of rotation. Then what we have is the moment of inertia of the disk is 1/2 mr squared, where that's the mass of the disk. The moment of inertia of the bullet is going to be, we're going to treat that like that is a point particle. We're going to have the mass of the bullet times the distance that the bullet is from the axis of rotation squared. This whole thing is the moment of inertia times the final angular velocity. We can simplify this part over here. That's going to equal -1. I can plug in values over here. I know the mass and radius of the disk. I know the mass and position of the bullet, so I can plug those in as well. Notice how small the contribution of the bullet is to the moment of inertia, so that's why we didn't worry about the details of it too much. But we can multiply all this out, and we find that the final angular velocity should be -6.23. Angular velocity should be measured in radians per second. It's negative because as a result of the bullet hitting up here, the whole thing is going to rotate this way, which is clockwise. So that's the negative direction, hence the negative sign. And again, we have the speed, the angular speed with which that disk is going to rotate.